So welcome everyone. The speaker today is Renata Turkeš, and she will tell us about, the title of her talk is on the unreasonable effectiveness of persistent homology in the natural and applied sciences.
Okay, good morning or good afternoon, everyone, and thanks for being here, and thank you again to the organizers for giving me the opportunity to talk at, as I already said, my favorite applied topology seminar. So today I will be talking about my most recent work on the effectiveness of persistent homology that has been recently uploaded to arXiv. So it is available if anyone is interested. We are now currently awaiting feedback from reviewers. So we're really trying impatiently to anticipate all the criticism that could be raised. So please, if you have any suggestions, comments or questions also during the talk, feel free to interrupt me. We're also trying to apply for some funding to bring this work further. So if you see anything that you think is missing, or you would like to see more things being done along this way, also any suggestions would be very much appreciated. What do I mean when I say we? So this is joint work with these two amazing people here, Nina Otter and Guido Montefar. I want to start with the motivation for this talk and also for this work, and also for the title itself. Basically, it is inspired, and all credits here go to Nina for this creative title, which is inspired by this old paper from Wigner from the 60s on the unreasonable effectiveness of mathematics in the natural sciences. Basically, Wigner there is discussing how a lot of mathematical concepts turn out to be useful beyond the context that they were originally developed in. So in the paper, you can find interesting sentences, like, for example, this one saying that the usefulness of mathematics in the natural sciences is something bordering on the mysterious, and that there is no rational explanation for it. Also, in the concluding remarks, Wigner says that the miracle of the language of mathematics for physics is a wonderful gift that we neither understand nor deserve. Now, how is this related to persistent homology? Well, I think most of the people here in the audience have seen a lot of papers out there which use persistent homology in a variety of applications. So from material science, neuroscience, biology, image analysis, and so on. However, the reasons behind the success of persistent homology in these applications is also a little bit mysterious. We don't really always understand why persistent homology works here. So basically, the goal of this work is to shed some light on this issue. So our starting question was, what kind of problems is persistent homology successful at tackling? And before I go any further, I don't know if there's anyone in the audience, I would be curious to know, that wants to chip in with their 2 cents on this question. So if you would have to give advice to someone to tell them when persistent homology works, for what kind of problems or applications, what would you say? I don't know if there's anyone who wants to share their thoughts.
I often say either you want to build filtration so that the bars are interpretable, you know what a bar is going to be, or alternatively, you use the bars as sort of some statistic of like not only global topology, but often local geometry.
Mm-hmm. Yeah.
So I think you sort of often want to be in one of 2 camps, build your bars to be interpretable from the start, or think of it as some geometry statistic.
Yeah, I mean, I would agree for sure with that, but these are still somewhat vague. I mean, topology and geometry, I think we wanted to gain a bit more insights beyond that. But indeed, I do agree. So before I go into the work itself, I just wanted to provide a very intuitive description of persistent homology, because I think most of the people here are familiar with the concept. So basically, persistent homology is capturing information about k-dimensional cycles, which are just connected components, holes, voids, or cycles of higher dimensions, in the so-called filtration, which is a nested family of spaces that are approximating our given X at different scales. And here is a small figure. So typically our data is given as a point cloud. And here, in order to extract this persistent homology information from this point cloud, we look at, in this case, the most common choice of the filtration, which is the Victoria strips filtration, whereas basically we construct an edge between any 2 point cloud points if their distance is smaller than the given threshold R. And then here, persistent homology is typically summarized with persistence diagrams, which are just scatter plots. On the x-axis, we have the so-called birth values, and on the y-axis, we have the so-called death values for each of the cycles in the filtration, right? So you can clearly see here that the zero-dimensional persistent diagram captures this one connected component of this point cloud, and it captures these two holes in the point cloud. Now, in applications, one rarely uses persistent diagrams directly because they're a bit nasty objects that don't have such a nice behavior. So commonly we vectorize these persistence diagrams into, for example, persistent images that are shown here, or persistent landscapes, which would be the most common choices, but there is a lot of different persistent signatures out there in order to be able to use them directly in machine learning pipelines. Now to go to the actual work, as I said, we are trying to identify some basically fundamental shape analysis problems where persistent homology will be effective or not effective. This is what we want to investigate. And we look at three different problems. So detection of the number of holes, detection of curvature, and detection of convexity. And every time we will construct some point clouds in R2 or R3 and try to classify them according to the number of holes, curvature, and convexity. We will evaluate experimentally the performance of persistent homology for these tasks, but we also compare them against some other basic machine and deep learning pipelines. Now, in the project description that I received, a short project description, it was also listed what the expectation is for each of these problems. And before I list them here, I also wanted to ask if there is anyone who wants to say what their expectation would be. So will persistent homology perform well for these tasks? If anyone wants to, is not shy. I see a one thumbs down. What does that mean? It will fail. Do you want to comment further? I mean, please.
I was just guessing that it would do fine with the first one and maybe struggle with the second two.
Okay. Is there anyone else who wants to add to that? Okay, I will just give here the expectations that were listed in the project description. Well, first of all, indeed, we would expect persistent homology to work well for the first class of problems. Why? Well, I showed you in the previous slide that persistent homology is precisely capturing information about these cycles, including holes. So if it's supposed to do well somewhere, it will do well, hopefully, for this task. For curvature, we also expect persistent homology to perform well. Why? Well, because there is a recent paper from Bubenik that, with the title Persistent Homology Detects Curvature, where they show both theoretically and experimentally that persistent homology can be used for curvature detection. And basically, we'll just replicate their experiments and try to gain some additional insights there. Now, the expectation that was listed for convexity is that both methods will fail. Why? Well, I guess just because we haven't seen anywhere persistent homology being brought up in this context of convexity detection. So it maybe seems counterintuitive that persistent homology can be used here. Maybe a small teaser before I move on. All of these expectations turned out to be quite untrue. Maybe it's not really fair to say that, but I will come back to that obviously later in the talk. Now, for the remainder of the presentation, I basically don't have almost any text. It's just going to be listing the figures from the paper. So we will go through these three classes of problems one by one. I will show you the data that we used, the persistent homology pipeline that we used, and then a figure with results. And then there will be just a summarizing slide in the end. Okay, let's go. First, the most easy problem, right? The detection of number of holes. This is basically the data that we look at. So I sample point clouds from these 20 different shapes that have either 0, 1, 2, 4, or 9 holes. And I try to classify this data with persistent homology. Moreover, I will also be adding some types of transformation in the data. For example, here I have some affine transformations for translation, rotation, stretch, and shear, but also these typical types of noise, Gaussian noise and outliers. Why do I do this? Well, because persistent homology is commonly advertised in the literature as a noise robust summary. So it is always interesting to look into this behavior of persistent homology with noise present in the data. This is the pipeline that I'm looking at in more detail. So it's pretty straightforward. So we start with, this is an example point cloud from our data set. And here I don't look at the Victoria strips complex, but rather the alpha simplicial complex, which is similar, just because I wanted to reduce the computational difficulty a bit. That's the only reason. I also do not look at the standard distance filtration function, but rather the so-called distance to measure filtration function, because we have outliers here in the data, and distance to measure filtration is precisely developed to be able to tackle these outliers. Then I extract one-dimensional persistent homology because we want to capture holes. Here it's the persistence diagrams, and you see these 4 holes in the point cloud clearly here. As I said, we don't work with persistence diagrams, but rather some other signatures. I will consider persistent images and persistent landscapes. These are the most common choices in the literature. But also I look at this very simple signature, which is basically just a vector of lifespans of the 10 most persisting holes. So lifespan meaning the death value minus the birth value. And you can see here that there are 4 holes that have quite prominent lifespans, and then maybe some other noisy holes that appear with very short lifespans. And I will use SVM to classify these point clouds based on these signatures. So I use here grid search in order to tune the parameters of persistent images and landscapes, to choose the best signature, and also to tune the parameters of SVM. Now, these are the results. So the different colors correspond to the different pipelines that we consider, and these will be pretty much the same throughout the paper. So the main pipeline of interest for us is the orange one, which is the persistent homology pipeline that I just showed you on the last slide. What I do, what is the experiment? Basically, I train each of these pipelines on 80% of randomly chosen point clouds, and then I test which are given in their original form. And then I test on the 20% of the remaining point clouds, but which can be also given in their original standard form, or they can be transformed according to these different transformations that we look at. And what you can see is that persistent homology is really performing very well for these tasks under every type of noise. Even this simple persistent pipeline where I'm just looking at the vector of lifespans. So I don't look at persistent images or landscapes. There's no need to tune parameters. I just look at the vector of lifespans that also performs pretty well. Now, why did I say that the expectation for this class of problems kind of failed? Was not true. You see here that, because you see here that the PointNet, which is probably our second most interesting pipeline, this is a deep learning architecture that was developed specifically for point clouds. And it is probably the one that is most commonly used for point cloud classification. So it also has a perfect accuracy here. So we cannot really say that persistent homology outperforms deep learning. However, you do see that the PointNet underperforms under certain types of transformations in the data. So persistent homology is indeed the winner here. Before I move on to the next class of problems, I just have a short remark that if anyone is interested in this particular topic of the noise robustness of persistent homology, my previous paper that is also available online focuses precisely on this issue. So in this paper, I tried to investigate what these stability theorems mean in practice, and in particular to highlight how their interpretation depends on the choice of application, the choice of filtration, and the choice of persistent signature, but also the choice of noise that you look at. And here I consider this most well-known image data set of handwritten digits. This is just one example figure from the paper. Obviously, we will not look at it in detail, but for example, one thing that you can note here that, for example, for the grayscale filtration and for persistence diagrams do change under certain types of noise. So you see additional holes appearing, for example, here. And the behavior is different across filtrations, signatures, and noise. But the paper is out there if anyone wants to look into that in detail. We move on to the curvature detection. So the data set that we're looking at here is exactly the same as the data in Bubenik's paper. So we are considering unit disks that are sampled from manifolds with negative, 0, or positive curvature. So negative curvature would basically be just like a potato chip, let's say. Here we have a unit disk in the Euclidean plane, so 0 curvature. And then we also look at positive curvature. Basically, in this case, unit disk would just lie on the top of a sphere with a certain radius. This is a screenshot from of a slide from one of Bubenik's earlier talks, which really gives good intuition about why persistent homology is successful here. So if you just look at these 3 triangles that are lying on manifolds with different curvature, you can really see that the length of the edges in this triangle, which is reflected in the persistence, is really related to the curvature. And in Bubenik's paper, they really provide a formula that explicitly connects the persistence to the curvature, and they also demonstrate this with experimental results. The pipeline here is quite similar to the pipeline we've seen earlier. Here, I just don't build the filtration directly on the point cloud, rather on the distance matrix. Why? Because we have the unit disks lying also on manifolds with positive or negative curvature, so spheric and hyperbolic distances are more appropriate here than Euclidean distance. And then I extract both 0 and 1-dimensional persistence diagrams, the same as Bubenik, and we transform that into these different signatures that we considered before, and again use SVM to perform the regression task in this case. So here are the results that basically show the regression lines for the different pipelines and their mean squared error. The pipelines that are of biggest interest for us now here is this central column. So the 0 and 1-dimensional persistent homology. And you can indeed see that, especially for 0-dimensional persistent homology here, it is really good in detecting curvature. We have true label on the x-axis and predicted label on the y-axis. In particular, it is definitely outperforming all of these other machine and deep learning pipelines. There was an extra thing that we did on top of the experiments in Bubenik's paper, which you can see here. So here we have the results when we only consider the 10 most persisting cycles. Now, why did I want to do that? Well, because one of the main insights that we have from Bubenik's paper is that these short intervals detect geometry, and in particular that the many short intervals together detect geometry. So I just wanted to make sure that this is true. So to see what happens if we discard some of the short intervals. And here, for example, the first regression line here is related to the pipeline where we just look at the lifespan of all the cycles. And here we just look at 10 longest lifespans. And you can indeed see that the performance deteriorates quite a lot. So all these short intervals do matter. Basically, that's the conclusion. Why did I say here that the original expectation was wrong? Well, just because in the, yes.
Yeah, we do have one question in the audience. So for the machine learning neural networks approaches, are the model features just the coordinates of the original points?
No, so for the machine learning pipeline and shallow and deep, which are basically just feed-forward neural networks, the input is the distance matrix. So the pairwise distances, I mean, I just look at the distance matrix above the diagonal and then flatten into a vector. That's a very good question. PointNet, on the other hand, directly takes the point cloud points, so the coordinates of the point cloud points. So it's specifically designed to take them as raw input. I forgot to mention that, so thanks a lot for bringing that up. And now did I want to say something else here? No. So yeah, why was the expectation from the project description kind of wrong? Well, in the initial rounds of experiments that I ran on very small subsets of data, I was able to also achieve a very good performance for PointNet that was just never replicated later in the final rounds, but maybe it's something that I would look into a bit further. But in this case, indeed, persistent homology is outperforming the other ones. Finally, we move to convexity, which I think is the most interesting just because this is new and I haven't seen it discussed in the literature before. So we think of this as our biggest contribution for this work. This is the data set that I'm looking at here. So first of all, I started with some what I call basic or standard shapes. So for convex shapes, this would be triangle, square, pentagon, and disc. And then I have their concave version. So some kind of a concave triangle, concave square, concave pentagon, and so on. However, we soon realized that this is not really enough and that it's better to diversify our data set a little bit more. Why? Well, if we just looked at these basic shapes, we would be left unsure if our pipelines are actually learning the shapes themselves and just discriminating between them, or are they really learning how to distinguish between convex and concave? So for this reason, we also introduce a lot of these, what I call random convex and concave shapes, and they're all different. These are just some examples that you see here. So what is my idea for the persistent homology pipeline? Here, I want to look at the height filtration, which basically is scanning the point cloud, for example, from top to bottom. Why? Because if you have a convex shape, this scanning will always only see one connected component. However, if the shape is concave, at a certain time in the filtration, you will have multiple connected components. A picture is always better, right? So this is the pipeline here that we use. So first I transformed the point cloud into an image because I'm looking here at cubical complexes. And then I look at this height filtration, but from 9 different directions that are shown here. Why 9 different directions? So if you look at the first row here, we are scanning this point cloud or this image from this top left corner. And it's slowly appearing, but we always have this one connected component. However, if we do it a bit more clever for this point cloud and scan from the bottom, so this direction here, you will see that for a certain time in the filtration, there are 2 connected components that eventually merge into one. So then what I do is that for each of these 9 height filtration directions, I calculate a 0-dimensional persistence diagram because we just want to know about connected components. And unlike the previous 2 pipelines, I don't consider persistent images or persistent landscapes here because I don't really care about all of these birth and death values and all of these details, because I'm only interested if there is a second component that will be seen somewhere in the filtration. So for example, here you see that this persistence diagram, it's related to the first row here. It only captures the one connected component. However, this last direction here, we clearly see a second connected component there. So basically my signature that I'm gonna be using here, I start with storing the lifespan of the second most persisting connected component for each of the 9 directions. So I will end up with 9 numbers. I can look at this vector of 9 numbers as my signature. However, I simplify the pipeline even further. I just look at the maximum lifespan across the 9 different directions. Why? Well, because I just care if there is concavity in the shape. I don't care if there's concavity from all these different directions of these little dents. If there is a concavity from at least one direction, the shape is concave. So I just look at the maximum. This scalar could also be used as some kind of measure of concavity because the bigger it is, the bigger is the concavity. And again, we just use a simple classifier SVM for this. These are the results. I look here at the 4 different experimental settings. So the first one is the easiest one that I mentioned in the beginning, where I just look at those basic shapes. So if you remember the triangle, the square, the pentagon, and its concave versions, and both persistent homology and PointNet perform perfectly here. However, when we move to any of these more difficult scenarios that also include these random shapes, persistent homology still performs really well, but PointNet starts, the performance of PointNet starts decreasing. Basically here, it's pretty much not doing anything. For example, this would be the most difficult case where we train our pipelines on these regular basic shapes, but then test on random shapes. Yeah, so I guess it's obvious here why the expectation that both methods fail is turned out to be wrong. I just have here this one extra slide for convexity, which shows some examples of point clouds where our persistent homology pipeline misclassified them as convex. So for example, here you see that none of these directions that we considered was able to capture this source of convexity. You would actually have to have a direction kind of going from here and then like this. But this is not really an issue because we can always add more height filtration directions. So our work on this problem was more a proof of concept. So to show that persistent homology can be used to detect convexity. But if you really need in your application to squeeze out a better performance, if a higher classification accuracy is needed, one can always add more height filtration directions. Which brings me to the final slide, which summarizes the work. So basically, the experimental results that I showed you demonstrate that persistent homology can be used to detect the number of holes, curvature, and convexity. Now, these insights helped us to do something more, two different things. First of all, we were able to derive some applications, we were able to derive some guidelines for the use of persistent homology in applications, which are kind of summarized in this diagram here. So if in your application, you know that the important information, so the information that is differentiating different classes of data lies in the number of cycles, the curvature, or the convexity, you can definitely use persistent homology for this application. And then the choice of filtration and persistent signature needs to be adapted according to this signal. So here we just basically summarize briefly the pipelines that I showed you earlier. You can also make some adjustments to these guidelines. For example, if you know that in your applications, both curvature and convexity could be important, it is possible to just concatenate these two pieces of information and work with all of this together. Now, second of all, our findings also help to extend this discussion about the topology and geometry that is captured with persistent homology. So persistent homology has been introduced as an extension of homology, which is a topological invariant. So probably it was also introduced with the idea to capture topology in the data, and it is often referred to in the literature as a topological summary. Often it is said, long persistent intervals capture topology, short persistent intervals are noise. However, this discussion has been refined through the years, right? So now we know, as Henry was saying in the beginning, that persistent homology can capture both topology and geometry, especially we have seen this with Bubenik's paper that I mentioned. But now kind of the statement is formulated along the lines of long persistent intervals capture topology and many short intervals together capture geometry, which is indeed the case in the two first problems that we look at. So you'll see here that it's the longest intervals that are capturing a topological piece of information, and many short intervals together are capturing a geometric notion of curvature. There's also this very nice recent survey paper by Henry Adams, where they really look into some important works from the literature to highlight this issue that I was just talking. Long equals topology and many short equal geometry. However, this third class of problems that we look at helps us to refine this discussion even further, because here you see that it was only one short interval, second longest, but short interval that was giving us all the information about the convexity or concavity. And in the appendix of the paper, we provide some more examples and try to play around with the statement. So for example, we give a hypothetical cancer application where only one and the shortest persistent interval is capturing all the important information for that application. So I want to end there, besides just also listing the references. As I said, this work is summarized in a paper that is available on arXiv. The second work is this intermezzo that I was talking about that really focuses on the noise robustness of persistent homology. And the third one is the paper from Bubenik that I mentioned already a few times that was really essential for our second class of problems on curvature detection. Thank you all for the attention. And I also wanted to thank Fulbright for making it possible for me to do this work with Nina and Guido. Thank you.
So thank you. Now, before we get to questions, I would like everyone to unmute themselves so that we can thank Renata for her wonderful talk. Okay, so now it's time for questions.
I have a quick question, if that's okay.
Go.
Okay. So I was thinking about the different kind of questions that you had put in the list, and that convexity is a really interesting question that it seems topology is adapted to. And another interesting question, which I think might come up in data applications, is if you have a collection of shapes, maybe like an optimal transport or a Hausdorff distance to some reference shapes. So let's suppose I have two shapes, A and B, and I want to have a third shape in, like, is this closer to A or closer to B? Right, in some geometric sense, like a Hausdorff gram of Hausdorff, Earth movers distance. And the question is, do you have an intuition for whether or not this is something where a geometric method or persistence could do well, or maybe this is an area where deep learning methods have been effective?
Well, I think that indeed, like, we can use persistent homology for that as well, because we could look at these three objects that you were referring to, so the A and B, and then our object of interest M, as just like three disconnected components, and see where in the filtration they will be, they will start connecting to each other, which will be capturing this distance between them. So I do think that this is possible now with deep learning. So the problem that we would be looking at, I'm just trying to think, like, what would be the data set look like and what would be the desired output. So it's just, let's say, like, the label would be shape A or shape B, whatever it is closest to. Yeah, I think like PointNet, because PointNet is also like what we have seen, it's performing really well for a lot of these pipelines. Also, for example, here in capturing the holes, and I think also the connected components, it would be also able probably to capture these the information about these distances.
Maybe to refine the question, because you asked, like, what would be the differences?
Yeah.
Maybe this is not quite what I was saying, but maybe I have two measures.
Mm-hmm.
And I sample point clouds of 100 points from both distributions, like, and then the question is, which one did it come from? In other words, can you figure out where you sampled your point cloud from? And I think theoretically this has been thought about, but I don't know experimentally how persistence compares to deep learning, but maybe this is just too long of a
So
question.
to connect the particular cycles seen in persistence diagrams, let's say, to where they are in the, is that what you mean?
Oh, it's sort of like I have two processes for generating point clouds sampled from two different distributions, and the task is just to infer which, or like to predict which distribution I sampled from. And there's a lot of theoretical results in that space, but I'm not really sure if anyone has pushed the computational question very far or compared it to deep learning methods. So
yeah, I think like the PointNet in particular will perform really well here because it is doing well in learning the different shapes. So if these, I mean, the different measures, let's say, I mean, in this case, to use your terminology, persistent homology, I think it can go any way because it depends on what are the sources of difference between these shapes. So if all of these shapes, for example, have, let's say, one connected components and two similar holes, persistent homology might fail. So it depends. We come back to the summary slide that I have. It depends what is the signal in your data. So in your problem, what are the sources of difference between these shapes? So you saw also that PointNet, so the deep learning architecture was really able to do well here. So to really, in this case, we're just looking at those basic shapes. So we had triangle, square, pentagon, disc, and so on, and their concave versions. And PointNet can achieves a perfect accuracy there because it is really learning how to distinguish between the shapes themselves. However, if the shapes don't differ with respect to, for example, these pieces of information, it's difficult to say. I mean,
thank you.
sure.
I have a quick question, which is almost certainly stupid. So I'm sort of new to this field. So I work for a publisher, and we have all of our articles, and we embed them in some vector space. And I don't like higher homology, and I don't like concavity because these are sort of holes in our portfolio of articles. And so step one, I need to be able to identify these holes and voids and things. But step two is I need to tell people to write an article that will sort of kill that homology or kill that concavity. This solves sort of the first part of the problem. Do you have any ideas on how to go about like answering the question, like which points do I add to kill the homology, say?
Yes, that's a very, very interesting question. And it's something that we actually wanted to do maybe for this work, but figured out that it's out of scope because we think that's a research topic on its own that we are considering of investigating further. So what we were like, for example, what we want to do is to try to identify, let's say, the importance of point cloud points. So if you have here, let me just find an example of maybe this would be a good example. So try to see really what are the important regions in the point cloud that were responsible for labeling a point cloud in a certain way. And in order to do that, our idea was pretty much similar to what you were saying, like trying to see what happens if we perturb the point cloud in certain ways. So basically, to be even more precise, in what ways do you need to perturb the point cloud so that it gets classified into the other class? So in this case of convexity and concavity, it would be which points we would have to add here to basically close this gap, as you were saying. So to have the articles that will appear in these empty regions. So if you look at this point cloud here, for example, obviously, like if you just do small perturbations, it would be these regions here that you will have to perturb and move them here in order to go from concave into convex. However, this approach that we were planning to use for this has nothing to do with persistent homology. It's more inspired from the deep learning. I mean, basically just to try to look at where the gradient descent is the highest. So it's which perturbation will result in the biggest change of this function that goes from the input data to the prediction. But we realized that there was quite some issues. So for each issue, we were kind of trying to find a workaround But then this is something that we want to investigate further. But I don't have an answer for you at this moment, and I don't think persistent homology could be used for this. I'm not sure. But indeed, as you say, persistent homology can be used for the first part, and then the next part is also next part for me. But thanks for the question. That it's really interesting. I saw that there was also things in the chat. Ah, there's more questions. Yay. Yes, please go ahead. I saw someone on
Hi.
Hi.
Oh, maybe I may start.
Sorry, this is the whole Zoom meeting thing.
Please,
if I may,
go for it,
my question is really fast. I was looking at your paper and I don't think I saw this. Do you have any analysis on like runtime of these various pipelines? I'm just curious for like online applications, how they would compare.
Yeah, so in the paper itself, I both look at the computation time of each of the pipelines and also memory usage. Mostly because persistent homology is very often kind of thought of as really slow. So I wanted to also, it was important, and also memory consuming. So I wanted to also look into that. So for each of the different classes of problems, the paper also lists figures in the appendix that look into this. And persistent homology is by far the most computationally efficient out of the other ones. But that also depends on what do you look at. So for example, if you just train a neural network on certain data, and then you use this neural network to calculate the labels for you on the test data, it will be faster than persistent homology pipelines, because persistent homology involves all of this like combinatorial stuff. However, you need to tune your network, and you also need to tune the hyperparameters of the network, which take a very long time. So I split to be kind of fair, to have a fair comparison, I split the computation time into time that is necessary for training and then also for prediction. So overall, persistent homology is better than the other ones because there is no training there, no sufficient training. So, but like you can look at the results in detail also in the paper, they're there.
Thank you.
Hi, thank you, Renata, for this very, very interesting presentation. I actually have a question. I noticed that on your experiments, you have mainly done lower dimensions, like 2 dimensions, 3 dimensions, and so on. Do you have some insight, or have you explored anything on higher dimensions?
Yeah, another interesting question. Yeah, we didn't do that. We started with these mostly 2D point clouds because they're just the easiest to plot and understand and describe and so on. But I think, well, yeah, that all of these pipelines would work with higher dimensions. I mean, because so, for example, here, for the first class of problems, we just look at the number of holes, but we could look at the number of connected components or the number of k-dimensional cycles. Nothing, I don't think anything would change there significantly if we look at higher dimensions. Same for curvature, also for convexity. Of course, you do have to adjust the pipelines a little bit. So for example, for the convexity, you have to, well, first of all, I'm not sure about software. So I was thinking about 3-dimensional convex and concave shapes. And I think that Goody is able to calculate persistent homology on the cubical complexes in 3 dimensions as well. But if you would go to higher dimensions, I'm not sure if there's software available for this. But in theory, there is no reason why this wouldn't work. The only annoying issue is that for the convexity, you would have to have way more height filtration directions. So for the 2 dimensions, these 9 directions are pretty okay. But just imagine going through 3 dimensions, you would have to have way more directions. And then if you go to higher dimensions, this number could explode. I do comment in the paper, we could avoid this curse of dimensionality there by just looking at random directions. So instead of just like looking at these like equally distributed around the plane or around the 3-dimensional space, we could look at random directions. And at this conference that I attended last month, there I had a question about this and there was a discussion, and someone told me that they looked into this a bit, and actually quasi-random perform much better than random. I don't remember the exact numbers, but just for example, looking at 20 quasi-random directions was better than looking at 200 random ones. Quasi-random, I don't know much about it, but basically you're just trying to enforce that all these directions are not concentrated, let's say in one region, so that they're a bit spread out. So I think you can extend all of these pipelines, no problem, to higher dimensions. It's just here that you would have to look at more high filtration directions. And I'm not sure if there is software available beyond third dimension for this case. Maybe someone else can.
And probably the number of points is going to be larger, right? In order to find patterns, yeah.
Yes, okay. Indeed, definitely. This is also why, but like you can avoid these issues a bit. So for example, for the first class of problems I told you, I looked at the alpha simplicial complexes instead of RIPs, and they're much faster. I have some slides here in the appendix. I was comparing this a little bit. So you see the victorious RIPs and the alpha simplicial complex. I mean, the number of simplices and the runtime is really, really different. Then for the second class of problems, the curvature, I couldn't use the alpha complex because alpha complex really needs the point cloud points. So the X and Y coordinates, let's say. And in the curvature detection, I really had to use these distance matrices. So what I did there, instead of using Goody, which I started with, for that particular class of problems, I used RIPSer. Because RIPSer is, as far as I know, out of the softwares that I know, the faster for the calculation of persistent homology with respect to the RIPS filtration. Yeah, so there's different ways to avoid this a bit. Sure.
Thank you, Renata. Great talk.
Okay, are there any further questions? Okay, so in case not, then thanks to Renata again for the wonderful talk, and I'm going to stop the recording here, and then all questions can happen offline. Thank you.